Well, hi all, and welcome to my video on Topic 3, Unit 4, Mathematical Methods, and this is on discrete random variables. So this is outside of a probability review, this is the first content that we really cover. You'll note here that I've got some resources here, success criteria, learning goal, and resources from the Cambridge text that we're using here at school. So I'm just going to run through some stuff to do with discrete random variables first, and this leads into something called Bernoulli distributions in probability, which leads into binomial distributions, and they're quite closely linked, and we'll get to those eventually. So let's start with discrete random variables. So a discrete random variable is discrete, and discrete, you recall, is something that's countable. It's random, so it's unpredictable, and it's a variable, so there's a range of possible outcomes, and that's why it's called a discrete random variable. We're pretty good at that in maths, in naming things very specifically after what they actually are. So an experiment can be a series of events, and I'll just make the note here that an event might also be called a trial as we get further on, events or trials. And we talked in a previous lesson about some probability review, so I'll be assuming some probability knowledge here. Now let's take flipping a coin 4 times. What could happen, and what is the sample space? Now I've written this sample space, and it took me a bit of time. You can see I've noted there ouch, and that's really important to note that takes us a long time to write out and to get an understanding of. And the question, what could happen? This question here, it's really important because the what could happen might vary on how you're actually viewing the outcomes of this event. So we could ask what could happen, and we could list 16 events there, 16 different things that could happen. But in some instances, some people might say, well, this event means the same as this event, for example, because it really depends on your viewpoint and what it is that maybe this game, this activity, this thing in life is what the actual outcomes mean. And so in these two events that I've highlighted, they both have 3 heads and 1 tail, and it might only be important to know the number of heads or the number of tails, and the order doesn't matter. And there's an example of that similarity, that situation. So you've really got to take into account what's actually happening. When we talk about discrete random variables and binomial probability, we're going to head more towards that, an understanding that in this case we have 1 tail. And you can see 1 tail occurs there, it also occurs here, and it also occurs here. And you can kind of see why it happens only 4 times, because that's when the tail is the first, that's when the tail is the second, that's when it's the third, and that's when it's the fourth. And then there's other options there as well. So this will be really important to understand that number of things. And let's have a look. In this case, as I've just said, order is irrelevant. We just want to know how many heads in this case that we get. That's all we care about. So here's what are our possible number of heads for 3 coins flipped? And the possible number of heads, we could get none, we could get 1, we could get 2, we could get 3, or we might get really lucky and get 4, but that's unlikely. Now if I go back to my sample space, and I'll zoom out here a little bit, you can see that how many ways could I get 4. Sorry, 4 heads, let's do that. And there's 1 way of getting 4 heads. How many ways of getting 3 heads? I've already highlighted those, and there's 4 ways of getting 3 heads. How many ways of getting 2 heads? So I'll highlight those in a different color. There's 2 heads, there's 2 heads, there's 2 heads, there's 2, there's 2, and there's 2. There are 6 ways of getting 2 heads. How many ways of getting 1 head? There's 4 there, and then there's 1 way of getting 0 heads. And you'll notice here that the total is 16, which is what you would expect, because we could see there were 16 in the sample space in each case. Now over here in purple, you can see I've used a couple of symbols. But firstly, yes, we know it's discrete data because I can get 0, 1, 2, 3, or 4 heads. I can't get 3.5 heads. We know that each event or each outcome is random, so we don't know whether we're going to get a head or tail each time, and each outcome varies. We've seen that as well. So therefore we say that x, so we're calling the variable x is modeled by, or is approximately equal to, that distribution of this. I use this a lot, and you'll see this a bit, a hash instead of number. So x is approximately equal to the number of heads in 4 coin flips, and it's a discrete random variable. So this is what we're going to be working with. Can we sketch this? Yeah, we can sketch this, and we get a really nice sketch. So if I put 0, 1, 2, 3, 4, 0, there's one way, then there's 4 ways, then there's 6 ways, then there's 4 ways, and then there's one way. 0, 1, 2, 3, 4, and it looks like that. Now it doesn't make sense to connect the dots because it's discrete. So again, I don't get, we might say, well, 1.5 is going to be about there, but I can't get 1.5. So it doesn't make sense to connect the dots, so we don't. But we can still see, and keep in mind I'm not connecting the dots here, we can still kind of see that really nice symmetrical shape, bell curvy sort of shape. And we expect this because in this case, the probability of a single head in one coin toss is a half. And because we've got a 50-50 chance, we expect that symmetrical probability. When that probability changes, we get a skewed probability. So we might get something more like this. If there's a low chance of getting a head, well, we're now more likely to get 0 heads and 1 head there maybe, and 2 heads here, and 3 heads here, and 4 heads here, and it looks more skewed. So that will vary depending on what the actual probability of one event is, or one outcome in an event, whether we get that nice symmetrical look or whether we get the skewed look. So let's have a look at example 1. A bias die is rolled 3 times such that the probability of each number R, and here's my probability listing, let Y be the number of 3s obtained in 3 rolls, so I probably should have a little less there, in 3 rolls of the dice. Determine a probability table for Y and sketch a graph of Y's distribution. Use the table to calculate the probability that Y is greater than 1. So let's just add a little bit of space here and we can roll through this. Now I might do this in a slightly different way. I might actually build up a one of these things that you know about, tree diagram. We're talking about 3 events, aren't we? Here, and then here, and here, and then here, and here, and I feel like they're going to run in together. In fact, they are going to run in together, so I might just move this, make that there, and then make it there, and there, and then I can do this. Make that close, drop that down there a bit, and it's not ideal, but it will do. So you notice here, when I'm drawing my tree diagram, I get nice straight lines here and here. It's a really easy way to set it up because I see many students make really messy tree diagrams. So we can get a 3 or we can get not a 3. Remember, if we put a straight line at the top or if we do a little dash there, that means not 3. 3 or not 3, 3 or not 3, 3 or not 3, 3 or not. Sorry if you're getting a bit bored here, but I'll just finish it off because I'm on a roll. There we go. And now I can add some probabilities to these branches. It's not going to be unique. So it's worth starting over here, just right over on the side, or maybe actually up here. The probability of 3 is equal to 3/8. And the probability of not 3 is equal to 5/8. So I'm going to pre-populate this and also calculate my probabilities. I'll do one example for you. And that is if I put 3/8 here, keep in mind that these are independent probabilities. I roll the dice again and it's not going to change based on the previous result. And the probability of 3 times 3s is equal to 3/8 times 3/8 times 3/8. And that's equal to, well, I'll keep it nice and stretched along here. That's equal to 27 over 8 times 8 times 8, which is 512. So quite low. Okay, I'm going to pre-populate this and then I'll talk about it once I'm finished. Okay, so you can see the pre-population of the data there, and just to run through that really quickly with the yellow highlighter, I've got the probability here of 3, 3, not 3, which I've written in here, and I've done the calculation 3/8 times 3/8 times 5/8, which is 45 over 512. Now, this is 3, not 3, 3, which is actually the same. I get the same 3 fractions to multiply. So I've got 45 over 512 again. I've done the same thing there. And equally, I've got this one, and this one. And that leads to, remember we defined our variable y as the number of 3's obtained. And so if y equals 3, there is one way of doing that. And that's here. And that comes out as that. Y equals 2. There are 3 ways of doing that. Here, here, and here. And so it's 3 times that one probability, which is this. If y equals 1, there are 1, 2, 3 ways of doing that. 3 times that, which is this. And if y equals 0, we have our answer there. Graphically, just really quickly, that will look like this. We can get 0, 1, 2, and 3. This is our y, and this is our probability of y. And so our probability of y has a maximum of 1, of course. And I can plot these. So 27 over 512, let's say I'm going up in approximately 50 over 512. So 27 is about here. 135 is about here. 225 is about here. And then 125 is about here. So you can see that we can't connect the dots, of course, but we can see that slight skew this way because we expect to get less 3's. So actually I've done it back to front, my apologies, because that's 3. Got to be careful you don't do it back to front because I've calculated back to front. So 125 is there, 225 is here, 135 is there, and then 27 is there. So we've got the slight skew this way because we're expecting to get less 3's because the probability of a 3 here is less than the probability of a not 3. So we get a slight skew. The other question, of course, is calculate the probability that y is greater than 1. And here's where I get a chance to talk about the really important things. First of all, these probabilities, 27, 135, 225, and 125 all over 512, should add up to 1. They are all the possible outcomes. So if I add those 4 decimals up, or 4 fractions up, sorry, I'll get 512 over 512. Secondly, I can use that to help me with this question. So the probability that y is greater than or equal to 1 is equal to the probability that y equals 3 plus the probability that y equals 2 plus the probability that y equals 1, which is pretty easy because we've done these calculations anyway, but it's also equal to 1 minus the probability that y equals 0. So this is a really good use of that probability sum to 1 rule because this is a bit easier. I get 1 minus 125 over 512, and of course that's 512 over 512 minus 125 over 512. 512 minus 125, I believe, is 387 over 512, and so that's our probability. So there's some reasonably complex stuff there, but this is all building on a discrete probability distribution where we're dealing with a case we want to count the number of 3's, which makes it discrete and also a distribution that is random and a variable. So a couple of notes. First of all, note that the probability that x equals x has to exist between 0 and 1 because we're talking about probabilities and they can't be less than 0 or greater than 1. If it's really common to make a mistake here, it blows it out of that boundary and you know you've made a mistake, so be careful. And also the sum of a probability of x equals x distribution should be equal to 1, and it can be written in a couple of ways. So just remember, this is all about the fact that when you sum all the probabilities, it will be equal to 1. And here's the work that we've got set for 14C for this exercise, and that's the end of this lesson. All the best.